Oh, just as I said that, someone turned up. Okay. So we are working our way through, or will be once I've got all my windows. Oh, I lost a window. That's what happened. Yeah. Hold on a second. I've got one more window to open, and then I'm ready. Okay, we are working on using derivatives to help us figure out what the shapes of graphs are. At least that's what the heading is. There are two derivatives that we use. The one that, in my opinion, is the most useful for telling you the most amount of things is the first derivative. And the first derivative allows you to find the intervals, right, the values of x, where the function is increasing from left to right, it's going uphill, or where it's decreasing from left to right, it's going downhill. It even allows you to find local max, local mins, and horizontal points of inflection. And once you know where they are, i.e. the x coordinate, you can then plug them into the original function and find out what the maximum or minimum or whatever it is you're interested in. The second derivative is useful. It tells you less information, really, in my opinion. What the second derivative allows you to do is to find out where the thing is, you know, concave up, like happy face kind of shape, or concave down. And when they talk about inflection here, they're really just talking about, you know, a happy face turning into a sad face, right? So it tells you where that point would be. When I talk about a horizontal point of inflection, I'm talking about like x cubed. So there is a changeover, but it's a zero changeover, right? The tangent at that changeover point is zero. Typically, aren't inflection points at an angle most of the time, right? This very special case, which is this picture, this is called a horizontal point of inflection, just so that you're aware. Between just a everyday point of inflection, which is what the second derivative tells you, and a horizontal point of inflection, which is what the first derivative tells you. The first derivative does not tell you the location of a general point of inflection. You need to do the second derivative to do that. And there's a whole load of steps that we did last time. It's quite involved, you know, a lot of things to do. So I'm going to pick a nice polynomial because they're the easiest ones to do this with. And I don't know, I get a feeling I might have done this one. No, I think the numbers are different. Yeah, they look slightly different anyway. So I'm going to start with an example, which would be question 7. The function that we're going to find information about is a polynomial, 5x to the 4, take away 20x cubed plus 1. And the questions are only asking us to find intervals of where it's increasing, intervals where it's decreasing, and the local max and min. So we're only going to be using first derivatives. So first thing you do is differentiate and power rule, multiply by the power, reduce it by 1, multiply by the power, reduce it by 1. And style points become crucial in these questions. And in particular, factoring the heck out of it is very useful. So I'm looking at these two expressions, and would you agree you can pull out a 20x squared as a common factor? Are you comfortable with 20x squared as a common factor? So here is the first derivative factored as much as I can make it factored. And so now we look for the critical numbers. In this case, we only need to find places where the derivative is 0. So in this case, it's 0 and 3. And then I build what I call my table of signs. Can you remember this guy? And I put the derivative, and then I put the shape. And I have a guy at 0 and a guy at 3. Hopefully you can remember how we decide what these numbers, the blank ones, are going to be. For instance, what would be a good choice of x for here?
-1.
I'd pick -1. Try and pick numbers that are easy to live with. Theoretically, couldn't I have picked -412.1234 if for some weird reason I felt I wanted to? I wouldn't, but I could. How about this guy? What would be a good choice here?
1.
1, right? You don't need to do 1.5, right? Pick whole numbers. How about 4, because I'm lazy, right? Now, for every single one of those values, we are going to find the value of the derivative. Make sure that it's the derivative and not the original function. It's easy to make that mistake, right? It's the derivative that we use here. So I go over here and where am I going? I'm losing the place here. Y equals, and I'm putting in 20x cubed. Take away 60x squared. And then my table has been set up for about the last 2 or 3 weeks. But remember, just to make sure that's asked. And then any table, delete all the other stuff and put in -1, 0, 1, 3, and 4. And the numbers that I'm going to get are -80, 0, -40, 0, and 320. It's like I'm losing pens everywhere today. You can tell it's getting to the end of the quarter. All my pens keep drying up. Right, so shape. That's negative. That's obviously 0. That's negative. That's 0 again. And that's positive. If one of my critical numbers was an undefined, wouldn't an error maybe appear here in some cases? Not all the time, but it could. Right. So everything I need to know is here. I tend to draw, because I'm a visual kind of person, an extra little number line. And I put in 0, and I put in 3, and I put there's a 0 there and a 0 there. And this guy here is negative. This guy here is also negative. And this guy here is positive. And just to remind you, only put the critical numbers down. Don't put these other numbers because they distract you. If you've only got the critical numbers, you're more likely to pick the correct intervals. So they want to know when it's increasing. Well, it's increasing from 3 to infinity. And when you do increasing and decreasing, it's always curved brackets, no matter what. If it's decreasing, the derivative is negative, so here and here. But there's a little gap in the middle, and you have to accommodate that. So here is negative infinity up to 0. And then from 0 up to 3. Are you all comfortable with the fact that that get broken into 2 separate intervals and a little gap at 0 because you can't use 0? So far, so good? Right. Now, let's find if there's any local max or mins. Right. Negative, sloping down. 0, and sloping down. Wouldn't that be called a horizontal point of inflection? Right? That's what they look like, right? Coming down. So that's, we're not interested in that because they don't ask about this. Then it goes negative, 0, and positive. So what's happening at x equals 3 is a local min. You agree there's a local minimum, right? A little happy face shape. And so I have a local minimum. For local max, since they give you a box for the answer to go, you just put inside the box that it doesn't exist, right? There is no local max. And for the local min, you do not put the value of x. You don't even put the coordinates. What you put instead is the value of the function at 3. And the value of the function at 3 means this guy up here. right? What the y coordinate at 3 would be another way of saying that. So let's do it. 5 times 3 to the power of 4, take away 20 times 3 to the power of 3, add 1, and the answer is negative 134. Are you comfortable with the process that we went through here to answer increasing, decreasing, and local maximum?
So for the local minimum, we just plug in the x value into the original equation?
Yeah, to this guy up here. So essentially, the value of the function at 3. Because if you put in the coordinate 3 comma negative 134, WebAssign will say that you're wrong. If you put in x equals 3 or just 3, WebAssign will say you are wrong. But if you type in just the number negative 134, it will tell you you are correct. So it's a case of answering what they were asking, and they're asking for essentially the y value. Now, if they wanted to know that guy 3, they would have to phrase it something like, what is the x coordinate of the local min, right? They'd phrase it something like that, right? And then you'd know to put in 3 if that's the way I asked it. Are we good so far? Right. They don't ask in this question, but I think since I've started it, let's use it to find concave up, concave down, and points of inflection, right? Let's go for that. So I've already got the original question, right? That's the original function. And I've just found the first derivative, which is that guy. And now I'm going to find concave up and concave down. So step 1, find the second derivative. Right? Power rule, multiply, reduce the power by 1, multiply, reduce the power by 1. Factor the heck out of it, so that's the style points. I think you can take out a 60x, and that leaves you with x minus 2. The process is going to look almost identical to this process. How you interpret the tables, the main difference, right? So when I look at this, would you agree that x equals 0 and x equals 2 are the critical numbers in this case, right? The places where zeros are. I'm not worried about undefined, they're not going to be any. I'm then going to set up my table of signs with a 0 again and a 2. I'm going to now do a second derivative, and we're going to talk about shape. Same kind of choice. You want a guy over here. Let's just call it negative 1, 1, and 3. Does that seem reasonable? Nice, easy numbers, nothing awkward, right? Negative 1, between here and here, 1, after 2, pick 3. And now I have to go to my calculator, and I have to put in the second derivative. So that's 60x squared, take away 120x. And then I go straight into this fella and delete the other question. And I'm going to put in negative 1, 0, 1, 2, and finally 3. And the answers I get are 180, 0, negative 60, 0, 180. And that's positive, that's 0, that's negative, that's 0, and that's positive. So far, so good. I mean, it's almost a carbon copy, isn't it, of this table? I'm doing the same kind of things to get the same kind of numbers. And these are referring to the value of the second derivative. These are referring to the value of the first derivative. So we are going to interpret them differently. So that's 0, and that's 2. So second derivative. On here it's positives, here it's negatives, and here it's positives. So how do we interpret them? Well, we're going to find the intervals where it's concave upwards, where it's concave downwards, and the coordinates of the points of inflection. So when you do points of inflection, you do it by giving the coordinates. So let's look at concave upwards. Should the second derivative be positive or negative when it's concave upwards, when you've got a happy face going on? Positive or negative second derivative? It's just a matter of memorizing Friday, because I'm sure I told you once. 50-50 guess. You want to guess? Positive or negative? Concave upwards.
Concave up.
Is positive or negative second derivative schedule? Which one is it?
Positive.
Yes, it is. It's not mathematical, but I think positive is happy, so it's concave up, right? And negative is sad, and that's concave down. So that's a way to remember, right? Concave up, you're happy, plus. Concave down, you're sad, negative. Right, so you're going to be concave upwards. Anybody in this region, which is negative infinity up to x is 0, and anybody from here onwards, which is going to be 2 to infinity. Are you comfortable with the positives, concave ups? And the negatives are from here to here. So 0 to 2. So that's what your answer is going to look like. What values of x is the curve concave up, and what values of x, interval of x, is it concave down? Now, the point of inflections happen here, x equals 0, and happen here, x equals 2. Can you see you're going from a happy to a sad face? Isn't that a point of inflection? And that happens at x equals 0. And there's another one at x equals 2. When you do local max and local min, don't you just put the y value in if they exist? But if you want to do a point of inflection, you have to put in the coordinates. So 0, comma, plug in here 1, and 2, 4, 8, 16, 80, 2, 4, 6, 120, that's negative 40, negative 39. So the points of inflection, or the coordinates of the point of inflection, would be 0, 1, and 2, comma, negative 39. And we're going to have to live with this because I don't really like it myself. When I write this down, these are coordinates. When I write this down, isn't it an interval? Don't they look exactly the same as each other? The notation's identical. The meaning behind them is what's different, right? This is all the values of x from 0 to 2. This is a single place, right? A single point with coordinates 0, 1. And this is a single point with coordinates 2, negative 39. So as long as you keep that in your head, that the notation that we use, the symbols that we use, although they look the same, have different meanings, depends on what they're telling you. It's awfully fast, I should put that back down. Are we cool with that question? Because I've basically done everything you could possibly do to a polynomial, right? Increase, decrease, and all the other good stuff. Rachel?
But at that point of inflection, would you, if you did draw a little diagram thing like you did with the other one, what would it look like?
It would look something like this. Can you imagine this is the origin, right? Let me take my information. It's negative on this side. So negative means it's a sad face, and then it would turn into a happy face. So the point of inflection would look like that. That's the first one. That would be, well, can you pretend that's 0, 1? Because I've moved it.
Okay, but you wouldn't do something like you did for the increasing and decreasing where you do something over.
I could. I'm not sure if it helps. I could do it and show you what it would look like. if you want to kind of visualize it. Happy face meeting sad face, right? Happy face is like concave up, and sad face is like concave down. So if you kind of put them together, can you see you'd get that shape? Right, and over here, it's a concave down, followed by a concave up. And if you put them together, wouldn't it look something like that?
Thank you. That helped.
I would have a guess that these two come together and make a big happy face, but that would be something else, some other thing. As I say, are we comfortable with that process? Because they take, as you can guess, it's took me over 20 minutes just to do one question, that I can't really spend a lot of time doing, a whole question from start to finish. So what I can do is maybe just pick pieces of each question that might cause you trouble to help you with it. So in question 8, the function that we're going to deal with is x to the 2/3 x take away 6, right? And this one, you're only going to be using the first derivative, right? So local max and mins and so on. But what I'm going to focus on is only one thing, and that is the derivative and the style points that come from it. If I left this guy alone, would you agree it would just be a product rule? And there's nothing wrong in doing the product rule, but the product rule would be really ugly. It just would be. And so I'm going to implement my rule called just because you can doesn't mean you should rule. So just because I can use the product rule doesn't mean I obviously need to every time. So I'm just going to multiply these out. And so I'm going to get 5/3 take away 6x to the 2/3. Would you agree that's easier to differentiate because it's just an ugly power rule? Now, it's not going to be pretty no matter what methods. Multiply by the power, reduce the power by 1. Multiply by the power, yep, and reduce the power by 1. And now we have style points. And this is where all the hard work's going to be. I am going to take that ugly mess and I'm going to put it together as a single fraction. So here goes. 5x to the 2/3 over 3, take away 4 over x to the 1/3. Are we cool with that step? You understand what I did there? A negative power became a fraction with a positive power. Now I have two distinctly different fractions here, but I want to join them to make a single fraction. And that means that I'm going to have to figure out what these two fractions turn into. And I'm going to multiply this by the special version of 3. And I'm going to multiply the first one with the special version of 1 called x to the 1/3. Do you see by doing that and that, can't they now share a common denominator? And the common denominator that they both share is 3x to the 1/3. And what does the top get me? Well, 5x to the 2/3 times x to the 1/3 gives you 5x to the 3/3, which is just 5x. And 4 times 3 is 12. Do you see the style points there was really ugly and really kind of weird? But haven't I got, that's as good as that's going to get, by the way. Now, critical numbers, because you need critical numbers, right? You build your table. There are going to be two critical numbers here. X equals 0 is bad. Would you agree 3 nothings is still nothing and nothing on the bottom is bad? Won't that be the place where the derivative is undefined? So there's one of my critical numbers. And the other one, well, whatever makes the top 0, and that ends up being 12/5. And that's the critical number because the derivative is 0. So these are the two guys that you're then going to make a table for, and then you're going to get the value, and then you're going to figure out pluses and minuses, and off you go and do what you need to do from there onwards. But that's still a lot of work to go, so I'm just going to leave it there. Any questions about what I did to get from here to here? Are you comfortable with the special version of one trick so that they share a common denominator, 3x to the third? Well, have you noticed that this guy gets multiplied by him and that this guy gets multiplied by him? Isn't it kind of you do what you've not got? You notice it's not random. Right, so if this was 7x and that was, I don't know, 5, wouldn't you give the guy an x and the other guy a 5, right? You would make them merge in some way. If that is okay, I will move on now. And let's look at question 9. And again, it's just setting up the derivative part. So we have an x squared take away 8 over an x minus 3. So in this question, that's how you could deal with fractional powers. In this one, I'm going to do a quotient rule, and I can't avoid it. See what we get then. The first derivative is f dashed g take away f of g dashed over g of squared. And the derivative of this is 2x, leave that guy alone, minus leave this guy alone, times the derivative of that guy, and square the bottom. Distribute 2x squared take away 6x minus an x squared minus a minus gives you plus an 8. Looks like we have an x squared take away 6x plus an 8, which is good, and an x minus 3 squared, which is good, but not perfect. Remember, factor the heck out of it rule. There's a lot of that going on in these questions. Can you see x squared minus 6x plus 8? Can you see the factors that you could get that into? X squared minus 6x plus 8.
X minus 4x minus 2.
I like it. How many critical numbers will this first derivative have? Just how many? You don't even need to tell me what they are yet, but how many are there going to be?
3.
Correct. The derivative is 0, gives you a critical number at 4 and a 1 at 2. And there is an undefined, isn't there? What is the value of x that would make this derivative undefined, uncalculatable, if you want to use that word? What's the x coordinate that makes this derivative undefined? I'll take an answer off anyone.
3.
Agreed. Right, now, I wouldn't normally do it, but for this one, I think I kind of have to. I'm going to set up my table, and it's going to be a 2, put a gap in, a 3, put a gap in, a 4, finish with a gap. I'm going to have my derivative, and I'm going to have my shape. And the reason I did this guy is because these numbers aren't going to make your choices, in some cases, easy. So let's take an easy one. What would be a good value of x for here, where my finger is pointing? Make life easy. What would go there? I didn't think that was too hard a question. What do you think goes here?
1.
1 or 0 if you like. This is the awkward one. Doesn't it have to be between 2 and 3? So there's no way of avoiding it. So being lazy, I just picked 2.5 and that happens. And between 3 and 4, again, being lazy, I'm just going to pick 3.5. But what about after 4? What would be a good choice?
5.
5, right. Feel comfortable about how you go from there onwards. Fill in the, use your calculator, find the value of the derivative at all these points, pluses and minuses, then decide increasing stroke decreasing, local max, local min, and all that good stuff. Oh, and by the way, WebAssign is quite fussy in quite a few situations. You're going to have to put exact values down, and that goes when you're doing your online test, which by the way is graded in online. So make sure that you, even if the answer is e squared minus the square root of 2, that's what they want, right? They don't want 1.234, which is what you might think. It also stops you just going to Desmos and drawing the thing, and then just getting the numbers off the graph, right? Because you could certainly do that for quite a few of the polynomial ones. Next one, still on first derivatives, as most of the questions are. This one is trig. And again, I'm only going to take it to the critical number stage. And we're only allowed to pick x in the region 0 to 2 pi. That's good, otherwise you'd have an infinite number of answers. Starts off relatively painlessly. You differentiate 3 sines, you get 3 cosines. You differentiate 3 cosines, and you get -3 sin x's. And now it gets awkward. I'm going to find critical numbers. I'm going to find when is the derivative 0. So that means I'm going to have to solve 3 cosine x, take away 3 sin x equals 0. I'm sure you could probably put that into a Desmos and get 1.377, whatever it might be, but we want exact values. I'm teaching pre-calc 2, I'm teaching trig this quarter. And so last week, was it? Maybe a little bit more than last week, maybe the end of 2 weeks ago, we were doing this exact type of question. What do I do to both sides to solve this equation?
Add 3 sin x to the other side.
That works. So 3 cosine x equals 3 sin x. Now, less obvious now. What do I do to both sides now?
Would you divide by 3?
Okay. And everything you've said so far is totally fine. You haven't done anything wrong. What should I do to both sides now? I'll give you a clue. What do I divide both sides by? There's not a lot of choices, agreed? What do I divide both sides by? If you hear a growling, it's my puppy annoying Bailey. Last chance. Hey, cut it out. He's annoyed at her. Come on, leave your little sister alone. Okay, here goes. I am going to divide both sides by cosine x. Well, let's see what happens. Cosine divided by itself is 1. From trig, what is the sine of x divided by the cosine of x? What is that equal to? It's a trig identity.
Tangent of x?
Yes. Now, I got a unit circle handy? I do. Hey, shush. Okay, we are looking for when is the tangent 1, right? Now, you can't really do your calculator because calculators give you 1.375s again, right? You don't want that. You want exact value. Does anybody know where on the unit circle a tangent of 1 will happen? There's actually 2 different places. And if you need a little bit of help, isn't the tangent the y coordinate divided by the x coordinate? So can you see any points here that if you took the y and the x and divided them, the answer would be 1? And I said there are 2 answers.
Pi over
1
4 and
pi over
then
4.
I hear pi over 4 twice, that's good. And the other one's in there if you look for it. You're right about pi upon 4, that is,
5 pi over 4.
yes, there you go. I know it's a while and you know you haven't done trig equations for ages and you only done a few days at most, and so it's a little bit of a culture shock to say what we need to solve trig equations. Nobody told me that when I took the class. Yes, you need to take trig equations from time to time, right? That's the guy that you're going to use. When you are creating your table of signs, when it is trig, as this certainly is, right? You might want to think about picking values here, here, and here that are also on the unit circle. They'll just make it easier to calculate, right? What angle is less than pi upon 4, but it's also in the unit circle? So what could I choose for the one that goes here? Less than pi upon 4. I could. And nothing wrong with pi upon 6. Why do you think I'm choosing 0 instead? Nothing wrong with pi upon 6, but why do you think I'm choosing 0?
Because it's easier to work with.
Easy to work with. That's the only. Be lazy, right? Lazy is another word for be efficient, right? You know it's easy to get 0 sines and cosines of zeros, right? Pi upon 4 to pi 5/4, right? So I've got from here all the way around to here. I can pick anybody from here all the way around to here. Pick something that looks easy. That's my suggestion. Which one looks easy?
Pi over 2.
That's one I would pick. Couldn't I also pick pi if I felt like it? That would work. Pretty easy one to do. What about the last one then? What would be a good choice? Anything after 5/4, which is here. Who could you pick? Anybody after 5/4 pi? Make your life easy again.
Could you do 2 pi?
Oh, you could. I didn't think of 2 pi. And nothing wrong with 2 pi, but that's the one I was thinking of. But 2 pi is fine. And you plug those guys in, won't you be able to get pluses and minuses and answer all your questions? The only thing that makes us a little bit different is you don't have minus infinities or plus infinities. Don't you have zeros and 2 pi? That's the end of the line, right? So when you're doing your intervals, it's going to be from 0 to somewhere, right? And when it's finished over here, it's going to finish at 2 pi, right? Because of that, right? That's the only reason. Oh, and by the way, you could argue curved or square on the ends. I don't know how WebAssign does it. I'll tell you right now, WebAssign makes them curved. So the rule is curve for everything, no matter what. Any questions about the trig one? Then let's do another trig one then. Yeah, last one for today. This is a version of question 12. F of x is equal to sine squared x, take away the cosine of 2x, and you're only allowed to go from 0 to pi. That's going to be important later. I don't need this line, but for some students, it helps. Isn't sine squared just the same thing as this guy, right? The reason why it might help you is, can you see it's a chain rule? It's a something being squared. So when you differentiate this, you're going to have 2 sine x to the power of 1 times the derivative of the inside function, which is cosine x. Take away. Now, if you differentiate a cosine, you get a negative sine of 2x times what? What's missing after you do the derivative of that negative cosine? You do get a negative sine, that makes it plus, and you do get a 2x, so I've got that. But what's missing? Yeah, you're missing a 2. Now, if I rewrite this a little bit nicer, again, taking my time. We got that. And yeah, you're going to have to work with trig identities. Can anybody remember the formula for the sine of 2x using sine x's and cosine x's? So what's the formula for the sine of 2x? We call it identity, but it's really a formula as well. Sine of 2x. Come on, get those cobwebs moving. What's the sine of 2x equal to?
Is that the 1 minus cosine x?
Oh, like 1 minus cos squared?
Oh, yeah.
I know where you're coming from, but that's what sine squared x is. So it's kind of,
Yeah.
but you're in the right ballpark for that, but not for this one. Sine of 2x, one last time. See, the point with me, if I just tell you, you'll forget it because you already forgot it. If you find it out in your head and you finally fight your way through, it's more likely to stick. So last shot. Don't care if
Okay.
it's wrong, go for it.
2 sine x cosine x.
And so 2 of them is going to now give me, I'm taking really, really slow steps here. Would you agree if you've got 2 of these, you've now got 4 of them? Oh, wait a minute, they're the same thing. So here is my derivative. And I'm now going to find my critical numbers, which in this case, I only need to find out when the derivative is 0, because that's never going to be undefined. And so I'm now going to be solving that. Any ideas what we do next? How would we solve this trig equation? What would my next line of working look like? I don't have enough time, so I'm going to have to just tell you.
Can you go backwards and turn it back into 3 sine 2x?
You could do that, and I wouldn't say that was wrong. I would just say that it's probably it is no quicker than what I'm about to do. If things are multiplied together give you 0, according to the basic laws of algebra, shouldn't the first thing be 0, the second thing be 0? You know, just like x times x plus 1 is 0, right? Factors get individually separated. Now, when is the sign 0? It's 0 at pi and at 2 pi. Great. And when is the cosine of x 0? And that's going to happen at pi upon 2 and 3/2 pi and a whole of the others. And then I factor in this piece of information. Doesn't it say 0 to pi? So forget about him. and forget about him because they're too big. So that means I'm left with these three guys, right? 0 and pi and a half pi, because they're the only ones that are in this range. And just to make life extra awkward at the end, when I build my table, it's going to look a little bit different, just a little bit different than the usual table. Right, here's my derivative, here's my shape, nothing special here. I'm going to go 0, space, pi upon 2, a space, and pi. Wouldn't I normally have an extra space here and an extra space at the beginning? Isn't that typical? Why am I not going to have a guy here and maybe a 2 pi over here? Why am I not going to have those? There's a reason for it. Why am I only looking at values from 0 to pi and not anything beyond pi or before 0?
Because of the parameters set in the beginning.
Right. And when you're doing this question, then won't your intervals be things like from 0 to pi upon 2 and from pi upon 2 to pi, you know, something like that? Because you're going to finish at a 0 and finish at a pi, so you're not going to have any infinities for the same reason. And put your last name down, and I nailed it. 1250, bang on the dot. So tomorrow, unlucky 13. So hopefully somebody has got a good memory. Unlucky 13, you're going to tell me, because that's the question we're going to start tomorrow with. Okay, as soon as you've got your answers and you've got your last name down for attendance, unless you've got a question for me, bye-bye until tomorrow.
Thank you.
You're welcome.
I've got a quick question.
Yes, Natalie.
I'm a little confused on how you're finding the local minimums and maximums from the graphs.
Okay, so let's suppose I've got some numbers here like that, right? And I've got a 0 here, I've got a 0 here, and let's say a 0 here. And these are all pluses, and these are all minuses, and these are all pluses, and these are all pluses, right? Just as an example. So you get the answer about local mins and max from this picture.
Okay.
So this is how I interpret it. From left to right, it's positive, it goes up. Then it's 0, flat line, and then it's negative. That tells me that there's a local max. That's what they look like. And it's happening at x equals -1. And then I just find the value at -1. And whatever that is, that's the guy you put in the box for the absolute maximum. Right? So if it's, I don't know, 73, you put 73 in there, right?
Okay.
Now, let's see what's happening at 0, right? It's negative, so sloping down from left to right. 0, horizontal, and then positive. Well, when it looks like that, we call that a local min. Local minimum, right? And there's a local minimum then at x equals 0. So we've got a local max here. We've got a local minimum here. And I'm saying absolute, that would be local here. Right? We don't know absolutes. And there's going to be a local minimum. And we find the value of the function at 0, and let's say it's 31. So it'd be a local minimum at 31. Of course, you could get this pattern, which is positive, so it slopes up from left to right, then it goes horizontal, and then it goes positive again. And when that shape happens, although WebAssign doesn't want you to give a name for it, we do have a name for it. That's the guy I call a horizontal point of inflection. But he's not any of these guys. So apart from knowing that's what it is, you don't really write any information about it down.
Okay. Are we going to get any, like, I don't know if you'd call it a trick problem, but maybe if after that 5 it went negative again, how would you tell from the
You wouldn't
maxes?
be able to. The cool thing is that if you find all the critical numbers, it can't be negative. And the argument goes something like this. Suppose somewhere way over there it went negative. Wouldn't it have to go 0? because you can't just go from pluses to minuses without passing through 0 on the way. And if you have to pass through 0, wouldn't there have to be a critical number that we would have found? And since we haven't found any more, because there aren't any more, that can't happen.
Okay.
So that's kind of the argument behind, once you know all the critical numbers, there are no more to find. And so shapes can't change from pluses to minuses because there's no way for them to be able to do it.
Perfect.
Apart from the ones that are there.
That makes a lot more sense. Thank you so much.
You're welcome. Okay, any more questions? Are you got a question for me? Teresa?
That helped.
Okay,
Nice same question. Thank you.
right, you are welcome. Bye-bye.
Bye.